In this video, we'll discuss about a new topic called fuzzy edge detection. These are our group members: Ankita, Manvi, Asif, Rohit, and myself, Rohith M. In this PPT, we'll see introduction, uh, brief explanation about our topic, and further, we'll see methodology, how it works, and the algorithm for it, and we'll see some results, and we'll conclude there. So, about the introduction, we have done edge detection, uh, which is a very important topic in image and image processing. It identifies significant local changes in intensity, serving as a key mechanism for extracting information. We have used content-based image retrieval, faces challenges, semantic gap and perception subjectivity, overcome by including classification and clustering, inducing logical information, introducing relevance feedback, and combining visual content with textual data. Also, we have used an enhanced approach utilizing type 2 fuzzy logic, offering superior handling of uncertainties associated with semantic image depiction. From here, Rohit Shirsat will continue.
Hello, I'm Rohith Shirsat. Now let's see the methodology. We have four detections: edge, corner, blob, and ridge detections. And we have used fuzzy logic involves grayscale conversion, median filtering, and Mamdani type fuzzy inference system for enhanced edge detection. It represents truth as values between 0 and 1 with variable membership functions. And the rule-based edge detection utilizes 2 by 2 mask sliding over the entire image and examining pixel values based on predefined rules in the FIS rule editor. It incorporates median filtering for refined and clearer representation of edges in the image. Further, Manu will continue.
So coming to the algorithm, we first have to apply fuzzification to our image. So first we convert our original image into a grayscale image and the matrix that our image will be converted to will have a range from 0 to 255. Now comes the fuzzification part. So we have a grayscale image already that is converted to a membership plane in the range of 0 to 1, as already explained by Rohit Shirsat, that the truth values are always ranging from 0 to 1, and it is done by fuzzy clustering. That is a fuzzy rule based approach and an integration approach as well. Now we apply gradients, and gradients are computed in both x and y direction. That means in our image we apply gradients in both horizontal and vertical directions. Then comes the fuzzy inference system. So in fuzzy inference system, we already have our input and the output image that we'll be getting are already 8-bit quantized. That is, they range from 0 to 255. So fuzzy sets represent linguistic factors. So what actually membership function does, let's say it has a linguistic variable known as temperature, and it has a fuzzy set hot. So as we know that it has truth ranging from 0 to 1, so it might assign higher temperature as a membership function value of 0. 0.8. Like for example, if we have coffee having a temperature of 40 degrees Celsius, so it might assign it a value of 0. 0.8, and somewhere between the temperature having 15 to 20 degrees Celsius, it might assign it a value of 0.3 or 0.4. So that's how the membership function works basically. It generally assigns, or we can say that it calculates the degree of membership that is associated with a particular set. So as I already explained, membership functions for output designed to separate values of black white edges in the image has been used. Now we come to the fuzzy inference rule. So this rule depends on pixel values of falsified input, that is the slope that we have obtained in the falsified image. So we have two rules in this problem. If gradients are low, then we consider the pixel background to be black, and the gradients are high, then we consider the pixel as edges. Now, as we have falsified the image and we have already applied fuzzy inference rule to our image, now comes the part where we have to defuzify the image to obtain the output. So, in the defuzzification function, we apply the Mamdani method. And then what it actually does, it converts the aggregated fuzzy outputs into a crisp decision by computing the centroid or center of the mass of the fuzzy set. So as I already explained in the example of temperature, it will be having many sets, for example hot, cold or moderate as well in case of temperature. So what it does is it takes decision, and it already has a set logic behind all those decisions, and it computes it decision by computing the centroid or center of the mass of the fuzzy set, and then it aggregates all those fuzzy inputs, which gives us the output image. So integration with unsharp masking, then what we do at the end is we integrate all of this with unsharp masking. So what we do is we use an image sharpening technique which is known as unsharp masking, which enhances the edge and sharpens it and suppresses the noise as well. So we could get a better picture of what we had given in the input, or what we are trying to identify. And all of this algorithm gives us an output that we'll be seeing in the further slide. Thank you. Ankita will be explaining the next.
Now let's see the results that we have obtained by applying the algorithm of fuzzy logic. So this is the original image that we have used. The next one is the grayscale image that is converted, and this uses like in the range of 0 to 255. These next two images IX and IY uh, are the image gradient, and this has been this has been this we have got this by applying Sobel filter. So Ix represents the gradient of the image in the x direction, where bright regions indicate a significant change in intensity along the x direction, and the second one, that is Iy, is the gradient, image gradient in the y direction. So bright regions indicate a significant change in intensity along the y direction. Next we have fuzzy edges. So fuzzy edges is the result of combining the both gradients, that is the Ix gradient in the x direction as well as the gradient in the y direction. So this indicates that the bright pixels indicate areas with strong gradients suggesting potential edges. The fuzzy edge 2 is the inverted part of the fuzzy edge. So here the black part is the edge and white is the background. Next we have implemented the sharpened image, that is here the sharpened image is created by applying unsharp mask to the original scale image. This process enhances the edges and details in the image, making them more prominent. So Mohammad Khalilul will explain further slides.
So there are different parametric standards that is used to measure the quality of resultant image. That is peak signal to noise ratio, mean square error, signal to noise ratio. Okay, this table shows the comparison of different methods on parametric standards. So now coming to the conclusion part, the algorithm is shown to produce better result in both qualitative and quantitative terms. The results indicate that the purpose fuzzy edge detection technique outperforms OTSU and Kenny methods in terms of performance metrics. Proposed methods has proven its capability in achieving better edge detection results, making it a promising approach in image processing. Thank you.